Okay, so the big picture of what DSP is all about is that you want to control or analyze real-world systems. And real-world systems are analog. So for instance, you want to control a robot's motion. You want to analyze a car's suspension performance. You want to create a new speaker system that, when you first turn it on, analyzes the acoustics of the room that's in, and then creates a perfect filter to correct for all the problems of the acoustic properties of the sound of the room that you're in. So you can do this using analog design, soldering transistors, but soldering transistors is hard. Or you can use digital design. Programming. And programming is comparatively easy. If you were to rip up that filter that you made in EE431 and rebuilt a new one, would take you hours. But to change a coefficient in a program and to reload it, upload it, might take minutes. So this idea about digital design, you're going to end up programming, idea is you're going to end up programming a microcontroller. And that leaves us with the DSP canonical system. And a canonical system just is the prototypic example for all systems. And that is that you've got some sort of analog signal. And maybe it's from a microphone or a sensor. And that analog signal goes into an analog filter. There's no way around this. You need the analog filter to cut down high frequency parts of your signal that you're not interested in before you bring it into the digital world. It's called an anti-aliasing filter. We'll talk about that in future classes. And you design that using techniques you already learned in signals and systems. Once that's done, you bring it into the digital world using an analog to digital converter. Now you'll do signal processing in the digital world, which is really programming in the digital world. And then you'll send it through a digital to analog converter. You'll send it through another analog filter. The first analog filter was called an anti-aliasing filter. The second one is called a reconstruction filter. Now you need some sort of analog amplifier. This signal will be very small and weak. You need to boost it up to control your analog device. So maybe it's speakers, maybe it's motors. This analog output filter is, again, a signals and systems course design. We've already talked about it. All you need to know is how to set the cutoff frequencies, which is in this course. This is a electronics class. where you built MOSFET amplifiers, BJT amplifiers. Everything in here is this class, all of DSP. So just as an example, your analog signal coming in might look like this. After the aliasing, anti-aliasing filter, it looks smoother. It gets rid of that fine stuff. Now, after the A to D conversion, you've got individual bits, more individual bits after your signal processing. Send it to your D to A, and now you have something that looks like discrete, a discretized version of a waveform. After your analog reconstruction filter, it's now smooth, and now after your amplifier, it's now big, and it can control your speakers or your motors. So again, that seems really complicated when you could have just had your analog signal go into an analog filter that does the right thing, and then send it back through an analog amplifier and you're done. But the reason why we have all this, center section is because it is so easy to modify our systems using changes in program, and so difficult to modify our system using changes in hardware. Okay. So I've got two more sections for you, both pretty small. The first is how to characterize a DSP signal. So a signal has two parts. In continuous time, it looks like this. It has this part, which is our independent variable, our time variable, and it has our output, which is our dependent variable. So in other words, in our continuous version, it's a mapping that maps any time t to, say, a voltage at that time t, and they're both continuous. Now turns out you can have either of them discrete. So your independent variable can be either continuous, which would be time. Wow, I don't know how I spelled that. Continuous, or it can be discrete. And then your dependent variable, your output variable, can similarly be either continuous or discrete. So as an example of one where it's continuous in, continuous out, might look like that. Here's your T, and I'll make this, instead of X or T, I'll make it a voltage. And this has a special name. It's called an analog signal, and it's what we analyze in EE431. Now, if your input is discrete, we'll call it N instead of T, because it's a number. No longer can you have a value at T equals 2.5. It's going to be it's going to be a mapping at N equals 1, N equals 2, N equals 3. And to show that N is discrete, we put it in square brackets instead of round brackets. And this is called sampled I'm sorry, let me try this again. This is called a discrete time signal. And this is what we are going to study in EE431. And as an example, your signal might look like that. For n equals 0, 1, 2, 3, 4, 5, 6. The vertical scale can be anything. It can be continuous, but the horizontal scale can only be discrete. Take a look and realize for a second that that allows you to store this signal. Instead of this continuous time has to be done graphically or as an equation, but this now could be stored as a vector of values. 1.2, 1.56, minus 6.3, and so on. And that's stuff that MATLAB can work with. That's something that your microcontroller can work with and process. Now, there are other types of signals too. There's a continuous time, but discretized output. So when it's discretized output, it can only be one of certain values. So now your signal might look something like this. It can transition at any point in time, but it can only transition between discrete values. This one's pretty uncommon. Now, in truth, when your computer stores information, it really stores it as a true digital signal, not as just discrete time signal. So it really does have a finite number of different ways it can store the signal. I mean, if it's using 64-bit arithmetic, as nearly everything does nowadays, it only has 2 to the 64th power of choices. Similarly, it's going to store your signal at whatever rate it's sampled. It might be sampling at every millisecond, in which case this n would correspond to milliseconds. And now your signal might look something like this. Okay, so this is the reality of what goes on in the computer. But somehow, instead of studying that reality, this course is about this approximation where we say the output can be any value, and it's only time that's discretized. The reason for this is twofold. The first is just because there's a beautiful theory that exists for discrete time signal processing. We can do it, and there is no great theory for digital signals. This one, the only way to really analyze it is to simulate what's going on. But in practice, this simulation, this world is almost just as good as theory. For instance, right now, your computers, they're all 64-bit processes. 2 to the 64th gives you many billions. It's greater than 16 billion combinations. That's a pretty fine degree here with over 16 billion lines. At that rate, there's no practical difference between a digital signal and a continuous output signal. And so that's why we use and so that's why this theory is useful. In all the years that I've been working, I have not found any time that the difference between, is that true? One time I have found a problem in all my years working in this field where what I expected to get using this analysis did not match up with my computer-generated results. And that was when I was using a 16-bit analog to digital converter over here. And I did a quick simulation to show that it was that limitation that was causing the problem. And then I just purchased, instead of a 16-bit, I purchased a 24-bit converter, and the problem went away. So that's the difference between continuous time and discrete time. And in this class, it's a discrete time signal processing course. Even though we call it digital signal processing, it's really discrete time signal processing. And then the only other thing I want to talk about, before I do, any questions on this? This is a nutshell of your first chapter in the readings. The first chapter in the readings, I would not spend too much time on it. It alternates between being overly simplistic and overly complicated, and it's really just meant to be a quick one over the world view of what you're going to cover in the course. So the parts that are too complicated because you don't yet have the theory for it. You'll learn it in the future. The only other thing I want to talk about is that this class is one-dimensional in, one-dimensional out. In other words, what goes in is one-dimensional and discrete, and what goes out, your X, is one-dimensional. It's like a signal, is what it is. But you can have things that are two-dimensional. For instance, you could have a one-dimensional in two. Let me think about this. You could have a two dimensions in, one dimension out. Here's an example of that. Here's your one thing out, and we're going to call it N1 and N2 in. So this might be an example of a voltage signal. This might be an example of an image. Now your N1 and your N2 correspond to your axes, N1, N2. And for every value of N1 and N2, you've got a number that corresponds to a grayscale encoding of the pixel image at that location. Here's a quick example of work that you can do in 2 dimensions. Okay, so this is a 2-dimensional image of a block and tackle system. If you high-pass filter that image in 2 dimensions, you get this. So this is before high-pass filtering, the original, and this is after high-pass filtering. And just like when you heard that signal earlier, that audio signal, when it's high-pass filtered, you heard the upper frequencies. Same exact thing is true for the 2-dimensional. 2-dimensional image processing is something that's more commonly done. That is covered in a graduate level topic.